This video is going to go over topic 9, which is center of gravity and centroid. Our objectives here are to discuss the concepts of center of gravity, centroid, and center of mass, and then solve a few problems where we can calculate these using a couple of different methods. A lot of this slide set should be a review from physics and calculus. If you kind of recall, in calculus, we use methods of integration to solve for center of gravity or center of mass, and we're going to use those methods as well today for this topic set. And we're also going to use some geometric methods that are a little bit simpler for kind of easy to calculate shapes like rectangles or triangles that you don't have to use methods of integration for. So let's start with kind of understanding what center of gravity is. So when we say center of gravity, this is a single point, and the resultant of all of the weights of particles of a body that pass through this one point, that point is called the center of gravity. And we're going to abbreviate that with the letter G. And also, one assumption we're going to make is that the pull of gravity is the same everywhere we're doing these calculations, which is fine for engineering applications. Here we have a pictorial representation of different types of systems. So the first system we see here in the upper left corner is a 1D system. So you could think of this like as a rod. And this is a segment that has a weight dW. So it's a small differential element, that weight dW. You can see here it's this little tiny portion. And it's located some distance away, which is this x tilde, some distance away. Okay, so what we can do is we can now use the method of sections, okay, and we can sum the weights of all of the rod's particles. So this here, this little red particle is one particle. On the rod. But what we can do is we can use the method of sections to sum all of the weights of all of those little particles of the rod, okay? And the center of gravity is measured from the y-axis, from this axis right here, this y-axis, okay, is determined by equating the moment of W about the y-axis to the sum of the moments of the weights of all the particles about the same axis. So we take this weight of the rod at some point G, okay, which is the center of gravity of the system. So I'm going to write that here. So what we can do to calculate this is we can say that W times x bar right here. So W times x bar, that's a function of moment, right? Because weight is a force and x bar is a distance. So force times distance, that's moment. That needs to be equal to the sum of all of the little weights times all of the little distances. So that would be this expression right here. I'm going to highlight for you in yellow. Okay. And basically, our x bar can be calculated now as the integral of all the x tilde, so the sum of all of these small differential elements, the distances away, this is x tilde, divided by the integral of dw. Okay, so this is for a one-dimensional system. I'm going to put 1D, one-dimensional system, okay? We can also do this for two-dimensional systems in a very similar manner, okay? But we're going to have coordinate pairs. So we're going to have x bar, y bar, and then if this is a 3D system, we'll even add in z bar. And this will give us a location of the geometric centroid for a 1D element, a 2D element, or a 3D element, okay? The next item that we need to discuss is the center of mass. So unlike the center of gravity, the center of mass is a specific point where the weighted relative position of the distributed mass sums to 0. So this is different because the center of gravity was the point where all of the sums of those little weights add up to that one resultant force, that one resultant weight. The center of mass is the point where the mass sums up to 0. And this is the point to which a force may be applied to cause some linear acceleration, but no angular acceleration. So this should be, it's kind of a little preview of dynamics, but also a little refresher from physics. okay? So we can determine this location by substituting, instead of using dW, which we used up here, we're going to substitute G, force due to gravity, times, or acceleration due to gravity, dm for the differential of mass, and we're going to substitute that into the equations that we had previously shown for a 1D, a 2D, and a 3D system. And if G is constant, which we're going to assume for the purposes of these problems and for all engineering applications, then we can cancel out G, right? Because we'll see it in the numerator and in the denominator, and we can get the location of the center of mass of a system by just the integral of x tilde dm over integral of dm. So instead of using the weights, we would use the mass, okay? So what you want to remember is center of gravity we're using the weight, center of mass, well, we're using the mass, okay? Now the centroid of a volume, if we have a body that is made of homogeneous material, and we're going to assume it has a density of rho that is constant, we can isolate a differential element of volume dV, which means that our mass would be equal, our differential mass would be equal to rho times our differential volume, so some small little element here. And substituting this into the previous equations here, okay, we would cancel out rho because we decided this is a homogeneous material, and we could also obtain formulas that can locate the centroid or geometric center of a body, okay? So here we have the geometric center, and these equations represent a balance of the moments of the volume of a body. So the moment, all these volumes, the moments about them, this is the balance point. If the volume possesses two planes of symmetry, then its centroid must lie along the line of the intersection of these two planes, just like you can kind of see in this 3D image here, okay? Now, this is centroid of a volume. We can also, so this is like 3D, right, volume. We can also do this for an area. This would be for 2D. And basically, this is something that we've all done in calculus. So we can evaluate integrals with a single integration if we use a small rectangular strip like this one. I'm going to highlight it. So we're going to isolate a rectangular strip. We could do a vertical strip, or we could do a horizontal strip like this, okay? If an area lies in the XY plane as such, like this area here, well, this blue area here, okay, and is bounded by the curve y equals f of x, this curve, then the centroid can be determined from the integral over the area of x tilde dA divided by the integral over the area of just dA, and that is for the location coordinate point of x bar. We can do the same thing for the coordinate point of y bar, okay? And x bar and y bar are shown here, the location of the centroid of the area. Lastly, we can do the same calculation for centroid of a line. This is for a one-dimensional system. And if a line segment or a rod lies within the xy plane and can be described by a thin curve y equals f of x, then we're going to do the exact same thing we had previously done, but instead of integrating over the area, we're going to integrate along the length of the element. So this is just one integration, right? This here is a double integral. And for 3D, it's a triple integral. Okay. So before we jump into an example here, some summary points. The centroid represents the geometric center of a body, and this point coincides with the center of mass or center of gravity when the material composing the body is uniform or homogeneous, which in most of our applications it is. The sum of moments to determine the location of the center of gravity or centroid. So to determine center of gravity or the centroid, all we have to do is sum moments. So we have to remember how to sum moments from our previous topics in this class. Let's go ahead and do a couple of examples. I think I have a few here. Okay. So example 1, locate the centroid of the rod bent into the shape of a parabolic arc as shown in this figure. Okay. So what we're going to do here is the first thing we can see is we can use Pythagorean theorem, okay? we can use Pythagorean theorem to calculate our DL. Okay, to calculate our DL here. And our DL is equal to the square root of, let me actually show you what DL is. So DL is shown on this diagram. It's this distance right here. Okay, so the reason we're using Pythagorean theorem is because you can see, we can kind of see this as a triangle. Let me put that in different colors here. Right? And you could see that this distance is my dx, and this distance is my dy. So I can use Pythagorean theorem, this is a right triangle, to calculate that DL based on dx and dy. So I would have dx squared plus dy squared. And make sure we know this is one term that's being squared. And now I can plug in here, right? I know the function of this curve, x equals y squared. So I know that dx here, I can plug in dx over dy squared plus 1 dy. Okay. And actually all I'm doing here, I'm just first dividing by dy squared to get this. I'm going to plug in the function of this curve, okay? But first what I can do, I also have to divide by dy here. Okay. Now what I can do, let me rewrite this. I have dl over dy equals the square root of dx dy squared plus 1. Okay. Now if I know that x is equal to y squared and dy dx equals 2y, if I take the derivative of this, then I can plug in dl is equal to, I can either keep the dy on the bottom here, or I can move it back over as it was previously put here. You can do either one. I'm going to move it back over for now, but I'm going to plug in 2y squared plus 1 dy. And now I know that the centroid of the element is x tilde, which is just the x location, y tilde, which is the y location. Okay. So I can plug everything in now for my previous equations for a 2D system. So my x bar function is the integral over the line of x tilde dl divided by the integral over the line dl. And so I can take the integral from 0 to 1, and I'm going to plug in what I have. So I have x times 4y squared plus 1. I'm just distributing in that 2. Okay. dy. Where did I get the x from? Well, x tilde equals x. So x tilde here, I'm plugging in for x. And here, this part of the function is the dl. Actually, I should circle the dy as well. This is all dl. Now, integral of just dl would just be integral from 0 to 1, square root of 4y squared plus 1 dy. And if I continue, integral from 0 to 1, I can actually plug in, I know that x is equal to y squared, so I can plug in y squared for that x. So I can plug in y squared here to get everything in terms of only one variable, so I can take the integral. And you can use your calculator. Just make sure you're using an NCEES approved calculator. Some of them will perform integral calculations for you, so you may want to start thinking about investing in one of those calculators, but you are welcome to use that for these integral calculations. This is a definite integral, so you can punch it right into a calculator, and you would get 0.410 meters. And remember, this is your x bar location. We still need to find y bar. Okay, so next we have y bar equals the integral from 0 or across L, y tilde dl divided by integral L dl. So we have the integral from 0 to 1 here. Instead of putting an x, I'm going to put a y. That's the main difference. And I'm still going to put my dl, which is the 4y squared plus 1 dy divided by integral from 0 to 1, 4y squared plus 1 dy. And I don't need to substitute anything anymore because I have only one variable here. So if I put this in my calculator, I get 8484 divided by 1.479 and a final answer of 0.574 meters, which is my y bar value. Okay, so that is the location of the centroid of this bent rod. Okay. Okay, so we have another example here, and we want to locate the centroid of the area shown in this figure. So this was a 1D problem. We're just doing one integral over a line. This is now an integral over an area. Okay, so I have two different solutions here that I want to show you, and I want to show you how you get basically the same answer whether or not you do this for a vertical or a horizontal element. So here we have a vertical element, here we have a horizontal element. You can choose either of those and you'll get the same answer. So let's start with solution 1, which is a vertical element for this system. Okay, so the first thing we see is we have this vertical element with a thickness of dx. Okay, and this intersects the curve at some arbitrary point xy. So you can see, I'm going to put it in red, this little dot. Okay, so this thickness intersects the curve at some arbitrary point, coordinate point xy. Okay, the height of this element is given as y. Okay, so our area and moment arms here, we have dA is equal to y dx. That's the function of that area, right? Because we have a height of y and a thickness of dx, so the area is just equal to y dx, the area of that shaded element. And the centroid, x tilde is equal to x, and y tilde is equal to y over 2. Okay, so we have x and y over 2 here. And you can see that here because the location of this centroid here, x tilde y bar, is in the middle of y. So this from here to here is y over 2. It's the centroid of that system. It's easy to see the centroid of a rectangle, but since we have this parabolic area under the curve, that's why we're going to split it up to all these little rectangles and then calculate that centroid. Okay. So now what we're going to do here, kind of section this off a little bit. Okay, we're going to take some integration. So we know that x bar is equal to the integral over the area of x tilde dA divided by the integral over the area of just dA. Now I'm going to plug in what I have in this side here. So I would have the integral from 0 to 1, right, for my x bar, 0 to 1 meter. And for my x tilde, I have x. right? And then for my dA, I have y dx divided by just the integral of 0 to 1 y dx. Okay, now I can continue here. I have an x and a y and a dx, so I want to put everything in terms of just one variable, which is dx, because that's what I'm integrating across. So here, I know that y is equal to x squared based on the area of the curve. I mean the function of the curve. So I'm going from 0 to 1 of x times x squared, which is x cubed dx, divided by integral from 0 to 1 of x squared dx. You don't really need a calculator for this one, but it's fine if you put it in as well. You get 0.25 divided by 0.333, and you get 0.75 meters for x bar. We can do a similar setup for y bar here. Integral over the area y tilde dA divided by integral over the area of dA equals integral from also 0 to 1 in this case. And y tilde was y over 2. dA was the same thing, y dx divided by integral from 0 to 1 of just y dx. And again, we're going to plug in our x values here. So integral from 0 to 1 of x squared over 2 x squared dx divided by integral from 0 to 1 x squared dx. And we end up getting 0.1 divided by 0.333, and we get 0.3 meters. Okay, so we get a location of 0.7, what's wrong with my 7? 75, 0.3. Okay, now let's do this, the solution 2 method, and let's show that we get the exact same thing. So in this case, we have our thickness equaled now to dy, and the length of the element, we don't have a height anymore, the length is given here as 1 minus x, right? Which means that our dA, the area of the element, would be 1 minus x times dy. Okay. Now, location x tilde is equal to here, our x tilde, this dot here, would be the x value plus 1 minus x divided by 2, because it's in the middle of the bar. And this basically corresponds to just 1 plus x over 2. And my y tilde would just be equal to y. This right here. Okay, so now let's go through some integrations again. We have x bar equals integral across the area x tilde dA divided by integral of the area dA. Let's plug in what we have here, 0 to 1. Our x bar was 1 plus x over 2. And then our dA was 1 minus x dy. A little longer this way, right? Not as fun. Integral 0 to 1 of 1 minus x dy. And then we have to actually keep plugging in here to make everything in terms of dy now. So I'm going to take that half out. It's a constant. Integral from 0 to 1 of 1 minus y dy divided by integral from 0 to 1 of 1 minus square root of y dy. And we end up getting 0.25 divided by 0.333, and we get 0.75 meters. Same as we got previously, 0.75 for our x bar. Lastly, let's do our y bar. Integral over the area of y tilde dA divided by the integral of the area of just dA. Integral from 0 to 1 of y times 1 minus x dy divided by integral 0 to 1 of 1 minus x dy. Let's plug everything in. We get the integral from 0 to 1 of y minus y to the 3 halves dy. Integral from 0 to 1, 1 minus y to the 1/2 or square root y, whichever way you want to write that. And we get 0.1 divided by 0.333, and we get 0.3 meters, and we end up getting 0.75, 0.3. Okay, so I think that the vertical element in this case was easier, but it really doesn't matter which way you choose to go. Okay, you should get the same thing regardless, right? Okay, so composite bodies. It's a good time to talk about wide flange beams, T-shaped beams, and different types of beams that we have in general, okay? So I have some pictures here. These are very commonly used in civil engineering applications, specifically in structural engineering applications. So this class is your first class of a series of classes where you will have to deal with a lot of beams and columns and shapes that are steel, concrete, timber, etc. So I have here a picture of a few wide flange beams all framing into a column. So I want to talk about what a wide flange beam is. You may have seen these in like construction sites if you've seen a steel building going up. You could also see these types of beams sometimes in parking structures. Even concrete parking structures would have these types of beams if you kind of look up and see how the beams are framing into the columns. But basically, we call these beams colloquially kind of I-beams. Okay, we call these beams I-beams, but more formally they're referred to as wide flange. And the reason for that is if I draw this beam as a cross section, this is the cross section, right? We call this here in the middle the web, and we call these top parts the flange. So you can see how the flange is really wide and the web is really skinny. So in the steel manual, these are referred to as wide flanges, and they're coded with a W for wide flange. Okay. We also have T-shaped beams because they literally look like a T. Okay. And this is the cross section of a wide flange beam right here. Okay. So what we have here is we need to calculate center of gravity, the center of gravity for these shapes really often, okay? But it's kind of tedious to sit there and perform all of these integrations to solve for the center of gravity. So what we do is we kind of have a simplification, okay? What we do is we split the shape up into really easy to calculate shapes like rectangles. So you can see how this T-shaped beam, we can kind of split it up into an upper rectangle that I've highlighted in red and a lower rectangle that I've highlighted in green. Okay, I'm going to show you how we get this formula in a second. But first what I'm going to do is I'm going to write down the formulas actually up here. So for composite bodies, we can use actually the following equations. X bar, these are simplifications, is the sum of all x tilde times w divided by the sum of w. Y bar is the sum of y tilde w divided by sum of w. And of course, this is for 3D element. Z bar is the sum of z tilde w divided by the sum of w. And x bar, y bar, z bar, these are the coordinates of G, your center of gravity, okay? And this x tilde, y tilde, z tilde are the coordinates of G also, but this is coordinates of G of entire composite shape, the whole T-beam, where G is. These are coordinates of G of each part or section of the beam. And sum of W is sum of weights of all parts. Okay, so I'm going to show you how to use these formulas without having to use the integral. Okay, but what we're going to do, I'm actually going to redraw this here here's the calculation for you. I'm actually going to start it fresh and redraw it so that we can see how this is done from the beginning, okay? So the idea is we're trying, here, actually I'll just draw it here. I kind of draw these big sometimes because we end up marking them up a lot. Okay, here is our T-shaped beam. Now let's give this beam some dimensions. I'm going to use the same dimensions that were given up there. I just want to redraw it here. So we have 7.25 inches, 1.5 inches from here to here, another 7.25 inches, and another 1.5 inches. Okay. Now, what we're going to do is we're going to refer to a datum here, which is kind of like our ground point, our 0, 0 point. So I'm going to use the bottom. You can always use the bottom or you can use the top. It's up to you. I'm just going to use the bottom. And what we're trying to do here is the center of gravity of the shape, it's not in the middle because the shape is not symmetric along the y-axis. So the center of gravity is going to be somewhere closer to the top because that's where more of the area is. So let's just say it's somewhere like, it'll be somewhere closer to the top, right? And it's going to be measured from the datum. So we're looking for this, and this is y bar, right? This is just 1D. This is a 1D problem. Most of these are 1D problems. Okay. Now, according to our equation, we're looking for y bar. According to our equation, y bar is equal to the sum of y tilde times w divided by the sum of w. And y tilde is the centroid of each part. So let's split this up into parts. Let's call, I'm going to highlight. So let's do a blue highlight here. Let's call this part 1. The blue part is part 1. And let's do the purple part as part 2. So we have part 1 and we have part 2. Okay. Now, y tilde for the blue part, I'm going to go to the blue section and cut it in half. My y tilde for the blue part is this distance. That is my y tilde for part 1. My y tilde for part 2, I'm going to cut the second part in half, measure it from my datum always, and that is my y2 tilde. Okay, so here you can easily see that my y1 tilde is just equal to, right, just equal to 1/2 of the 7.25, oh no, sorry, that's my y2 tilde, sorry. My y1 tilde, this blue one, is 7.25, this distance here, 7.25, plus half of 1.5. And that's equal to 8 inches. My y2 tilde is just 7.25 over 2, which is just 3.625 inches. Okay, now the weights in this case, since it's a 2D system, they are areas. So I think we can all calculate the area of a rectangle. It's going to be 7.25 times 1.5, which gives us 10.875. And then the purple area is the same, 7.25 times 1.5. Okay. Now all I have to do is plug this into my calculation. Now y bar equals y1 tilde, 8 inches, times area 1, plus y2 tilde, times area 2, divided by area 1 plus area 2, and I end up getting y bar equals 5.8125. So this distance here is 5.8125 inches from the bottom, because the datum was at the bottom of this. Okay. So now we've done a T-beam. This is the same calculation here that you can see if you wanted to see it here. Okay, I have it here for you as well. We're gonna do a couple of more problems. I'm gonna do example 3 with you, and then I want you to try example 4 on your own. So let me add a page here. Okay, let's do example 3. So now we have a wide flange beam or an I-beam. Okay, but we want to determine the location y bar of the centroid of the beam that has the cross-sectional area shown. We're going to do the exact same thing with this. So I'm going to split this up once again into, I'm just going to redraw it actually so I have a nice large shape to work with again. Okay, now let's give some dimensions here. We have 150 millimeters at the top, but we have 100 millimeters at the bottom. And this distance here is also 15. And what we want to know is, where is y bar? It's showing us measured from the top. You can do it from the top or the bottom. I'm going to do it from the top this time so I can show you. Actually, let's do it from the bottom. It doesn't really make a difference. So we're going to make this bottom our datum once again. And our y bar is going to be somewhere closer to the top here. We'll find this distance. Well, really, we'll be finding this distance. Doesn't matter which one you find. You can find this one or you can find this one. It's just subtracting the full length from it. So same thing. All right. So we're going to have this area here. Call this area 1. Area 2. And we'll do area 3, green. So we have area 1, area 2, and area 3. Okay. All right. So for our area 1, let's cut it in half. Measure the distance from that to the datum. Okay. So we basically have 150. So let me write this down. This is y tilde 1. Y tilde 1 is 1, well, we'll do 15 plus 150 plus 15 over 2, and we end up getting 172.5 millimeters. That's y tilde 1. Might as well do A1 as well, which is just the area 150 times 15 and we get 2250. Now let's do area 2, y tilde 2. Let's cut 2 in half, measure this distance, and we have basically 15 millimeters, 15 plus 150 over 2, and we get 90 millimeters, and our area 2 is 150 times 15, so we get 2250 millimeters squared again. And our last area we have, let's cut this in half, and this distance is just 15 over 2. So y, that's y, let me write that here. Y tilde 3 is 15 over 2. So we end up just getting 7.5. And then our area 3 is 100 millimeters times 15. So we have 1500 millimeters squared. So we can calculate our y bar from the bottom this time, same as last time, but calculate our y bar, 172.5 times 2250 plus 90 times 2250 plus 7.5 times 1500 divided by 2250 plus 2250 plus 1500, and we get y bar of 100.3125 inches. And that is our answer. Remember, that is this guy right here measured from the bottom. So if I wanted it from the top, all I would do is take my total length, 150 plus 15 plus 15, minus the 100.3125. So it doesn't matter if you do the top or the bottom. So go ahead and try example 4 now, and make sure that you can find the location of y bar. I will give you the answer. Measured from the bottom, y bar is equal to 216.29. There are no units for this one. Make sure you're able to get that, okay? That is the last part of this video. So go ahead and try these examples and stay tuned for the next video.